Today we are going to look on the effect of pH on the chlorine dose or the acidic or alkaline nature of water on the dose of chlorine. The use of chlorine has become practically universal in the disinfection of water, and the dose of chlorine which is used for the disinfection depends on the organic matter present in water to be disinfected, the pH value of the water, the carbon dioxide content in the water, the temperature of the water, and the time of contact of the disinfectant with water. Out of these, the pH of water has the most important role to play because the pH controls the dissociation of the hypochlorous acid, thus affecting the disinfection of the water directly. When the chlorine is dissolved in water, the hypochlorous acid is formed and the hypochlorous acid remains in equilibrium with the hypochlorite ions, and these hypochlorous acid HOCl and hypochlorite ions will remain in equilibrium as per the pH. Also, when the bleaching powder is added in water, the fresh bleaching powder contains about 33.3% of chlorine. It dissociates into hypochlorous acid and the calcium hydroxide, which will impart the permanent hardness to the water. The hypochlorous acid will also, in the case of bleaching powder, remains in equilibrium with the hypochlorite ions as per the pH. The killing efficiency of hypochlorous acid is about 40 to 80 times more than that of hypochlorite ions, so it is better to keep the chlorine in the form of hypochlorous acid as it is well suited for disinfection. Again, hypochlorous acid will have more killing efficiency and time of contact will both be less, which also depends upon the pH. The equilibrium constant is given by Ki is equals to the right side of the equation H plus OCl minus and the left side of the equation divided, which is HOCl divided. The equilibrium constant Ki for HOCl differs at different temperature. Rearranging the above equation, Ki by H plus is equals to OCl by HOCl. Now, taking the percentage of HOCl in the equilibrium, the percentage of HOCl is given by the total HOCl divided by the total HOCl and OCl both into 100%, which is HOCl divided by HOCl plus OCl. Again, rearranging, we get 1 by 1 plus OCl divided by HOCl into 100%. Now substituting this for the value of Ki by H plus, we get 1 by 1 plus Ki by H plus into 100%. Now we can get the percentage of HOCl by 1 by 1 plus Ki by H plus into 100%. The Ki is the equilibrium constant, which is constant for any temperature, and H plus is the hydrogen ion, which depends upon the pH, which is given by 10 to the power minus pH. Taking an example, at 20 degrees centigrade, the constant value of equilibrium constant is 2.7 into 10 to the power minus 8 moles per liter, and at pH 7, the percentage of HOCl is given by this formula, which we have seen earlier. Again, keeping the Ki equilibrium constant as 2.7 into 10 to the power minus 8 divided by the pH at 7 is 10 to the power minus 7, the hydrogen concentration. Now, the percentage of HOCl came out to be 78.7% HOCl, and the percentage of OCl will be 21.3%. At pH 8, the percentage of HOCl will be same as per the previous formula, keeping the Ki as 2.7 into 10 to the power minus 8 as the equilibrium constant, and at pH 8, the hydrogen ion concentration will be 10 to the power minus 8 into 100%, and it came out to be 27.03% HOCl, and 72.93% will be OCl minus. At pH 9, the percentage of HOCl will be 1 by 1 plus Ki by H plus into 100%, which will be 3.5 7% HOCl and 96.43% OCl, as most of the HOCl will remain in the hypochlorite ion form, which is OCl minus. Again at pH 7, 78.7% HOCl and 21.3% OCl, which indicates the good killing efficiency, as HOCl is 40 to 80 times more efficient than OCl. Again at pH 8, 27.03% HOCl and 72.93% OCl, which is not very good. And at pH 9, all of the HOCl will remain as OCl, which is 96.43%, which is very worse. We can see that figure in the graph as well. In the case of 7 and in the case of 8 and in the case of 9. This shows that the pH highly affects the HOCl and hence the disinfection efficiency. Or else we have to provide the contact time much greater than the actual needed time. Example, if the contact time at pH 7 is 12 minutes, then the contact time for pH 8 will be around 60 minutes, and for the pH 9 the contact time will be around 21 hours, which is very high and not possible. Also, if the chlorine dose at pH 7 is 0.6 mg per liter or milligrams per liter, then the dose of chlorine at the pH of 8 will be 1.75 mg per liter, which is very high for same disinfection. Then the dose of chlorine at pH of 9 will be 13.3 mg per liter, which is very high, and this form of chlorination is not feasible, and other forms of chlorination in the form of chloramines or other forms of disinfectants will be applied at this pH range. Also, calculating the bleaching powder requirement. The bleaching powder chlorine content is generally about 23.3% in the fresh condition, and if the water to be disinfected will be taken as 40 lakhs liter of water per day for 40,000 people with 100 LPCD water demand. At pH 7, the bleaching powder needed will be 7.2 kg per day. At pH 9, the bleaching powder needed will be 160 kilograms per day, which is very high. So this form of chlorination or bleaching powder at this amount will not be done, and other forms of disinfection should be applied. And in conclusion, the pH highly affects the efficiency of free chlorine. The dose of application of chlorine is highly affected by the pH. The contact time should be increased for the same disinfection efficiency. If the pH is very high or very low, other disinfection forms or chloramines will be applied. Similarly, this concept is applied for drinking water and in swimming pools disinfection also. This way we conclude the effect of pH on the dose of chlorine. Hope you like the content.